Hello and welcome to our webinar series called ChemInfo Stories 2020, where we share development news and user stories about Chemaxon's technology solutions. My name is Dora Barna. I work in Chemaxon's application scientist team, and I will be the presenter of the workshop today. This is the 7th day of our webinar series, and in this session, I will show you how we can use Chemaxon's Design Hub solution for chemical lead optimization and compound tracking in early phase drug discovery projects. Before we start today's session, let's do some housekeeping. First of all, privacy. You are in a Zoom webinar now. This means that you have accepted and understood Zoom's and Chemaxon's privacy policies. This means that your personal identifiable information, such as your name and username, depending on which one you use for the registration, may be visible to other attendees in the platform. You are responsible for any content you share. We assume no liability for confidentiality. To minimize the potential risks from this, you are all muted, your cameras and chat are blocked. We do have, however, a Q&A button at the bottom of the Zoom screen, where you can type your questions, which we will answer in writing or live during the Q&A sections. So keep an eye out for the chat channel, because we will be sharing relevant information with you there. And as we have most of the talks pre-recorded or like this one are recorded during the session, we can send you materials really quickly in a follow-up email. I hope this will continue to spark discussions with Chemaxon and also among each other. Our LinkedIn users group serves a platform where you can ask your questions, share your opinion, and you can also connect with speakers. We are sending the link to the group in the chat just now. And now some practical information about the workshop and today's agenda. First, we will start with a short presentation where I'm going to give you an overview of Design Hub, tell you about its key parts and how they can be used in preclinical discovery. Then we will go to the application and continue with a demo of using Design Hub to capture new compound ideas and to characterize, prioritize, and drive forward these new molecules, the new molecular ideas. Because of the online webinar format, we cannot have a classic hands-on session, workshop session today. However, we still wanted to give you the opportunity to try out this new solution, either by following the demo or even after that. Therefore, we shared with you the details of where and how you can access Design Hub. These details were sent to you in an email yesterday, and you can find the same information in the chat window as well. But to make sure that all of you can log in without any problem, let me summarize the steps here as well. So first, you have to create a Chemaxon account if you don't have one yet. For the account creation, you can use the URL that you hear on my slide or in the email I mentioned or in the chat window, and also in the automatically sent invitation message that we sent out when we registered you for the workshop. Please make sure that you use the same email address for the account creation with which you have registered for the webinar session itself. And once you have created your Chemaxon account and got the email with your password in it, you can use your email address and this new password to log into our Synergy demo platform using this second URL. And after the login, you can open Design Hub and go to the application with which we will work today. Once in Design Hub, select the Sign in with Chemaxon Pass option and pick a name that you would like to use as your display name during the workshop. And with this, you are all set and ready to start using the Design Hub solution. So for the rest of the workshop, feel free to listen to the presentation and the demo afterwards. But I would encourage you to log into the application and at one point to get some real hands-on experience with it. This demo environment will remain available for the upcoming 2 weeks. So if some features or some solutions raises your interest, you will be able to come back in one of the following days and try it again. After this introduction, let's see what is the Chemaxon Design Hub. The short answer to this question is that it is a preclinical team collaboration platform that supports the design and management of new compound ideas. However, the design of new chemical structures is only one part in a much larger and much more complex process, because each new project starts with a goal which can be related to a new observation or a new interesting idea or hypothesis. And while the chemists are working on and collecting the scientific rationale to explain their observations or to validate their hypotheses, they collect more and more new ideas in the form of freshly designed virtual molecules. And once they have collected all of these ideas, the chemist team has to use the available data to prioritize these ideas, these virtual molecules, and to decide which of these virtual molecules they want to synthesize next in order to run new experiments on them and collect further data, which eventually will get them closer to either confirm or reject their original hypothesis. And during this process, it's important that the chemists can track their virtual molecules to know what is happening to them, what kind of decisions were made about them and why, and what should be the next step as the project keeps moving forward. So what Design Hub does is that it provides a single platform to research chemist teams that connects the scientific rationale with the designed virtual molecules and with the tools and computational resources to have all existing and predicted data available for the triage of the compound ideas. So how does the workflow behind Design Hub look like? First, we have to summarize our hypotheses and the observations we have made and capture the details of the related scientific rationale. And based on this hypothesis, we can start working on our initial compound ideas and then continue with refining the structure of these initial ideas in step-by-step manner. And while working in this structure refinement, the chemists have to consider a large number of molecular properties and parameters so that at the end, they will have a molecule, a virtual molecule with good or promising attributes, which later they can expand into a series of structurally related virtual compounds. And while they are working on this, other chemists in their team may start looking at a different idea molecule using another chemotype or different modifications. So at the end of the day, the team will have a large number of virtual compounds which have to be prioritized, and the decision have to be made which of these virtual molecules will be synthesized next. So they can run new experiments on them and use these new experimental results to refine and update their hypothesis in the next iteration. We have now seen the workflow of Design Hub that we will also follow today. Let's continue with taking a closer look at the individual steps in the process. As we have just seen, the first step would be capturing the details of our initial hypothesis. But before we do that, we can take some time to browse the research and design history that has been collected over time. For this, we can use the application's search capabilities to look up previous and still ongoing projects to see whether someone at our organization has already had a similar idea to ours, or if they have worked with the same target or with similar compounds that we are interested in, or we can check if in general there is anything useful that is related to our topic. And once we have checked the repository to collect information about historical and ongoing research activities, we can really start working on the hypothesis, on the new hypothesis, and capture the scientific rationale that gives the foundation of our new project. For this, we may use any kind of information, any kind of existing information, such as already available structure-activity relationship data from previous studies or from the literature, or we may already have some 3D structural information about the target we are interested in. All of these can be collected with the multi-purpose hypothesis sketcher of Design Hub, which allows us to summarize everything we know about our topic in a graphical format by adding structural information, measured data, X-ray structures, and so on. And after we have captured this existing information, we can use it to start working on our first virtual molecules using the design mode of the application. This design mode allows us to sketch new molecules, to refine the structure of these new compounds, and to create a list of promising virtual molecules. And by working on this structure refinement, the design mode also makes it possible for us to check how the key attributes of our virtual molecules are changing. This way, we have immediate information, immediate feedback about the effect of each structure modification step that we have made. And this can be achieved by using Design Hub's plugin system, which can connect us to various pieces of existing and predicted data from different sources. This system is a service-agnostic solution to plug in any kind of data source or predictive tool we would like to use while designing virtual molecules. In this workshop, we are going to use publicly available data sources and models, besides some of Chemaxon's own property prediction tools. However, the system can be used to plug in in-house or proprietary databases and predictive models as well in much the same way. Another advantage of the plugin system is that it gives real-time feedback. So as we are drawing a molecule, the plugins will immediately update themselves and display the results of our latest structure modification steps. And finally, this is a dynamic system where the plugins can be switched on and off depending on what kind of information we want to see. And this helps us to ensure that we always see the right amount and the right kind of data, and we can avoid this way getting overwhelmed with too much information and with too much noise. So let's continue now with a couple of examples to see what kind of properties and data sources we can use for structure optimization in the Design Hub. When working with virtual molecules, we frequently have to check key physicochemical properties of our molecules to make sure that they fall in the desirable property space. For this, we are going to use Chemaxon's property calculators. And these calculator tools will also help us to check other parameters of our molecules, such as the pH dependence of their calculated log-D values or their CNS MPO score. These property calculator plugins can also be used to directly compare our ideal molecules to other reference compounds that are important for some reason. And besides these key medicinal chemistry related properties, we can use existing 3D information as well. The plugin that we will try out today is using the calculated 3D alignment between our ideal molecules and the known ligand of our target protein. to see how our virtual molecules would fit into the protein, the target protein's binding pocket. For this, we will use publicly available data from the protein data bank, and we will visualize the overlaid 3D structures in the protein's active site. Design Hub can also give us useful information about toxicity-related questions. One of its plugins that is called hERG Assistant gives us suggestions about possible structural modifications which could help us reduce the hERG liability of our virtual molecules. The Assistant plugin was built on top of a matched molecular pair-based knowledge base for which we used publicly available assay data, and we also collected statistics for a large number of, for almost 200 high-frequency chemical transformation. If you want to check whether there is some assay data already available for our idea compounds or for molecules that are close structural analogs of our ideas, we can use a plugin based on the Campbell bioactivity database. This way, we can find any existing biological data related to our virtual molecules, or we may get new design ideas, or we can simply make sure that our virtual compounds have not been tested yet against our target protein that we are working with. Another way of getting inspiration by designing new molecules and finding potential new ideas is by searching in large virtual or real compound libraries. In this workshop, we are going to use the Enamine Real database for this, which contains more than 1.2 billion synthetically feasible molecules. With the help of this Enamine search plugin, we can use similarity and substructure searches to find new compound ideas which may have modified scaffold or different decorations. And finally, we also have to think of how and where we can access the molecules that we have designed, whether we can purchase them from a supplier, or how difficult it is to prepare them in the lab, or where can we find the building blocks for their synthesis, and so on. To answer these questions, we can use the Design Hub plugins that are connected to different supplier catalogs. We can check, for example, if our molecules are available for purchase in the eMolecules catalog, or if we can find their building blocks to synthesize them. And during this design process, we can collect a large number of virtual molecules. And in order to have a better overview of them, we will organize these compound ideas into design sets, which also makes it easier to explore the virtual chemical space around our hypothesis. Besides organizing the virtual molecules, Design Hub can be used to register them as well and assign virtual identifiers to them, which makes it easier to track these virtual molecules and to have discussions about them while they are going through the different steps, including design sessions, team discussions, prioritization, or when they are finally selected for synthesis. And when we have collected every idea, we have to decide which molecules we want to take to the next stage, which ones should be synthesized, and which are the ones that need further refinement. To do this idea triage, we will filter our compounds based on different properties, such as their chemical constitution or their physical chemical attributes. And finally, we will sort them based on some key parameters to find those ideas that should get the highest priority. And as we collect more and more compounds, create further and further design sets and hypotheses, each with their own priority and their own state of completeness, it becomes more and more difficult to overview every research activity within a project or or at an organization. To get help with this issue, we will use the Kanban board of Design Hub that gives us an up-to-date summary for each project regarding, for example, the priority and status of the different items. The Kanban board can be combined with various filters to find out how our compounds are progressing, what is the status of our hypothesis, what kind of dependencies we have to expect, and where are the blockers in the system. So these are the key Design Hub parts we can use while working on new chemical structures. And as a next step, let's go to the application and continue with the demo part. And in this demo, we will go through a hypothetical scenario where we found some interesting information in a recent scientific article. And we want to investigate if, based on that study, we can design virtual molecules that could contribute to the optimization of a lead compound, which have the potential to be used as a therapeutic solution for Alzheimer's disease. The first thing we have to do is logging in to the Synergy Demo platform, where we have to use the email address and password of our Chemaxon account. And after the login, once we arrive to the Synergy dashboard, we will open the Design Hub application and select the Sign in with Chemaxon Pass option. When you log in for the first time, you have to select a name for yourself, a display name, and also a project or projects you would like to work on or which you are interested in. In my case, for example, I'm already following these 4 projects, but I could change them anytime, or if I come to this organization page. And once you have selected and saved your project selection, you will arrive at the hypothesis page if this is your first time login. In this hypothesis page, you will see every hypothesis that belongs to your selected projects. And from here, you can navigate to the applications dashboard by using the Design Hub icon here in the top left corner. And the dashboard of Design Hub contains all the recent information, notes about the recent activities, any kind of comments that were added, and you can also find information about the topics and items which are especially interesting for you. And you also get a brief summary about the key changes in the system. In my case, for example, I can see that in the 4 projects that I am following, 4 new compounds have been shared in the last 7 days, and 4 new compounds have been synthesized. All of these 4 compounds belong to the same hypothesis, where the topic is the design of some new aggrecanase inhibitors with improved selectivity. This hypothesis already have 4 design sets. One of them is still in the draft phase and contains 5 virtual molecules, but the other 3 are in more advanced phases. This one, for example, is already in the synthesis phase. And if we check the molecules, we see that 4 of its 5 virtual compounds are already in the synthesis phase at the moment. So at this point, we logged into the application and see where we can find new information, where we can find the hypothesis and the design set. So we will have a short 5-minute break now where we will check the Q&A section, and we will also answer them, and my colleagues will help you if you have any technical difficulties with the login or with something else. And once we are back after the break, we will continue drafting our first hypothesis. Welcome back to the second part of the workshop. As I mentioned before the break, our next step would be to start working on our new hypothesis. And this hypothesis will be related to the design of new molecules, which could have the potential to be used for the treatment of, for the therapy of Alzheimer's disease. But before we start sketching the actual hypothesis, we can check if we find anything related to this topic in the design repository of the application. So we can run a first quick check for which we will use the search box here at the top. And this way we can figure out if Alzheimer's disease has already been mentioned in any of the hypotheses in the application. So there are two hypotheses actually around this topic. This second one is related to some pharmacophore-based virtual screening, and it has a single design set which already contains a couple of molecules that are ready for review. And if you check the second hypothesis that is related to this topic, we find that it actually has three design sets. In one of them, the synthesis has already been completed, and there are some new molecules prepared from it, while the other two design sets are also in quite advanced stages, because they are the molecules that are either waiting for synthesis or are under synthesis currently. And actually both of these hypotheses belong to the same project, because both both hypotheses is about some acetylcholinesterase related compound. And now that we start our new hypothesis, we will also add this new item to the same project, the Cognition ACHE, because we also want to work on some new acetylcholinesterase inhibitors. And the basis or the starting point of our new hypothesis is a recently published article in which a small library of benzoic acid derived nitro molecules have been described, along with a lead compound, which could both inhibit the acetylcholinesterase enzyme and could decrease the oxidative stress in the cells. And this way it has the potential to be developed into a multi-target drug molecule. And the goal of our demo scenario today is to use Design Hub to create some new virtual molecules that could exhibit the same dual effect and meet the various criteria for drug likeness as well. So with this additional background information, I will now create my hypothesis in the already existing project. And the first thing is select a name for it. So I will call it multi-targeted acetylcholinesterase inhibitors. And then I will use the hypothesis sketcher in the application to summarize all the things that we know about the topic at this point. So the study that we are using as our starting point describes a small library of benzamide-derived nitron compounds. So in the first slide of my hypothesis summary, I will add a title about this. So benzamine-based nitrons with dual effect. I will also add some formatting, so make the fonts a bit larger and drag it here to the top of the slide. And then I want to add the generic structure that represents this compound library from our base study. So I will use the structure drawing toolbar of the hypothesis sketcher, and we'll quickly draw this generic compound. And I will also have to add some variations into it. So there can be some different functional groups here on the right-hand side. And the paper that we found describes molecules which contain a methoxy group in varying positions of the aromatic ring. And once we have drawn the generic structure, it could be useful to mark the different regions in it. So these compounds have three separate parts, separate regions. The first one, I will also add different colors then. The first one on the left-hand side is substituted aromatic ring. Here I will use some smaller fonts. Then in the middle, there is a spacer region, while on the right-hand side, there is a nitron moiety, substituted nitron moiety that is supposed to be responsible for decreasing the oxidative stress, so giving the antioxidant activity of the molecules. I would also like to add some notes to this first slide to have some information of what this multi-target effect means. So on the one hand, these tested compounds were able to inhibit acetylcholine esterase, and they also had some antioxidant activity. So this is the graphical summary of the key parts. And I can also add a textual description about what we would like to do, of what we know at this point, and what we would like to do, and what we would like to focus on. So what we want to start with, we want to investigate the effect of using, let's say, using different aromatic or heteroaromatic rings on the left-hand side of the virtual molecules. And then later on, we can continue using different substituted nitron groups. I will also add a reference to the original paper that we found, and this way we will know where we can get some additional information if we need them, and I will also add the link to it so it will be easier to look it up later. And now we are ready with the first draft version of the hypothesis. What we can extend the hypothesis with are some keywords or tags that later on would help with the searchability of this hypothesis. I can add some keywords to it like Alzheimer's disease or acetylcholinesterase inhibitor, or the keyword antioxidant, and finally last one, multi-target. So all of these can help me to look up the hypothesis and the information that I have added to it. And before we finish the first version, I will have to set the priority and the status of this new item. So at this point, it's still a draft. However, I will give it high priority and I will keep it assigned to me. And now we can close the editor. The first version of the hypothesis sketch is ready. And later on, if we collect further information about it, we should extend it and add this new data to it. For example, if we have some 3D information about the structure, the X-ray structure of the target enzyme and the active site on the target enzyme, we can add it to a second slide. So I will now import an image that displays the active site of the target enzyme with its known ligand, the donepezil molecule, aligned to one of the previously investigated nitron molecule. And if we think that the hypothesis contains already enough information to be shared with the rest of our team, then we can make it public. So far, it was a private item, so only I was able to see and edit it. But now I will share it. And at the same time, I will also change its status to ready for review. So other people in my team will know that they will have to check and review it. And after we finished drafting the hypothesis, we can start working on the design of our first virtual molecules. And the goal in this phase would be to test every possible chemical directions, every possible chemical modifications, and to see what kind of effect they have. And this way we can validate our hypothesis and check any assumptions that we have made so far. So in our first design set, we are going to explore what is the effect of changing the aromatic side of these nitron compounds. So let's create this first design set. Its title will be Aromatic Ring Modifications. And here I can add again a short description of what we would like to do here. Let's say it should be something like investigate what is the effect of using various substituted aromatic or heteroaromatic rings. And I will also add a drawing about the generic structure of the molecules that we would like to test here. So to make it quicker, I will go again to structure drawing mode, and I will import a structure file about a molecule which has been tested in the previous study that we have found. And in this phase, what we would like to do is changing this left-hand side of the molecule and try out different rings with different substitutions. So I will add the generic label here, and I can also add some information, like what kind of aromatic rings we want to investigate. So we can add a couple of them. We can try, say, a pyridine ring or an indole, like this. Or also pyrimidine if we want to. And as a finishing touch, I will again add some coloring, some highlight to emphasize that this is the part of the molecule that we are interested in at this stage. I shouldn't forget to add some keywords here as well. So we are working on nitron compounds, which will contain some aryl amide functionality. And we are still working with, or working to find acetylcholinesterase inhibitors. Say these three will do. And finally, the priority and the status information. So the priority of this design set should also be high, but we are still in the draft stage with it. So I will add the coding meta information, and let's check if we added everything that I wanted. We can now close the editor. We summarized the goal of this design set. So the next step would be to really start working on the virtual compounds. And for this, we can go to the design mode. And here in the design mode, we can either start drawing our molecules, or if we have some structure files with some compounds that we would like to try, we can import them. Or if we know that some of the other design sets contains interesting compounds, that we can also copy molecules from there as well. What I will do now is that I will import a single molecule, the same one that I've used at the design set drafting. And I will start, as a first step, I will start looking at different substituents, different functional groups to add to the benzenic carbon atoms. But in order to have some guidance here, I will use some property calculation plugins. For example, I will use a plugin that shows me the calculated physical chemical properties. And since we are looking for acetylcholinesterase inhibitors, it could be useful to check the CNS MPO score of the molecules, which could give us which could be used as indicators to give us an idea how probable it is that the design molecule will be able to cross the blood-brain barrier. And this CNS-MPO score plugin, besides displaying the final calculated score value, it also visualizes the individual values of the 6 physicochemical properties that contribute to the CNS-MPO value of the molecule. I will change the layout a bit because I want to add later further plugins, and I will need a bit more space. So I can add the second column, and I will drag and drop this plugin to here, the right column, and change the layout modification. So now we can start modifying and refining the structure of our molecules. For example, we can try what happens if we remove one of the methoxy groups and replace the other one with a hydroxyl group instead. What we can see from the second plugin is that since we added another hydrogen bond donor atom, that led to the decrease of the CNS-MPO score. So that's probably not the best direction so far. And if you want to use some further information here, then we can also define a reference compound to which we will compare the properties and attributes of our designed compounds. I will add the donepezil as my reference compound. I can pin it to my design page and then return to my virtual molecule sketch. And now you can see that both plugins are comparing the current and the pin structures and also indicating in which direction the properties are changing or differing. So we can now try a couple of other modifications. So adding one hydroxyl group actually decrease the CNS-MPO score, but we can try what happens if we add an alkyl group or even a longer one. And while we are using different functional groups, we can use the plugins that can give us information about any unwanted structural elements, any unwanted functional groups that we should avoid. For example, there is a PAINS plugin that we can use. This PAINS plugin looks for functional groups that occur quite frequently in so-called pan-assay interference molecules that react unspecifically with a large number of biological targets. So if we use this PAINS plugin, we can get alerts every time when we add such an unwanted functional group to our molecules. For example, if we add an amino group here, then we will get such an alert about this part of the molecule. So this is something that we better avoid, especially because it really didn't help with keeping the value of the CNS-MPO score at a relatively high level. So instead of using this molecule, I will try and close this ring here and see what happens. So we could remove the alert and also the MPO score looks a bit better. But if we want to get some 3D information about our molecule sketch, then we can open, for example, the conformers plugin that generates the various conformers of the molecule in the editor. And this way we can get an idea about the shape, about the 3D shape of the molecule, and also we can see what kind of conformational flexibility we have to expect. And to get more information about the 3D properties of our compounds, then we can use this alignment plugin here. And this plugin calculates the 3D alignment between a known ligand of a target protein. In our case, acetylcholinesterase, and the known ligand will be the donepezil molecule. And for this, we can use data coming from the PDB archive. So I will add the PDB code of the acetylcholinesterase enzyme and the donepezil molecule, and select the file format. And once we have the required structural data, then we will get a 3D image, an interactive 3D visualization of our idea compound, the light blue one, and the donepezil molecule aligned by their 3D structure and placed in the enzyme's binding pocket. We can change the display a bit, remove the cartoon of the protein structure, but add the binding site instead. And we can also visualize the most important interactions between the ligand molecule and the protein's key amino acids, key residues, and the water molecules that are present in the binding pocket. And we can also add some labels. And this way we can check that our compound, the light blue one, has an oxygen atom in the same position where donepezil has, and which is important to have a hydrogen bond with one of the amino acid residues. So it should be a feature that we should preserve by designing new compounds. So after all of this, if I find that I found an interesting compound that needs further analysis, I can save it and add it to my collection. I will save it as a draft. And now I have my first saved virtual compounds. And what I can continue with after that, I can try some further functional groups. For example, using a simple chlorine atom here. And also save it if I think that it's a good enough idea at this initial phase. So I can extend my collection with more and more items. But while we are doing this, we also have to pay attention some other aspects. For example, the question of toxicity. And to get help with this problem, with the problem of toxicity, we can use the hERG predictor plugin, which is a brand new addition to Design Hub. And it uses the first machine learning based property predictor that was developed by our calculator team. But this plugin does, and what the underlying model does, is that it calculates the hERG IC50 value of our virtual compounds and also our reference molecules and compares the two. And also gives some color-based indication whether we are still in the safe range with the hERG liability, or whether we are in more riskier territories. And we can also combine the results of this hERG predictor plugin with another toxicity-related plugin that is called hERG Assistant. And this HERG assistant is the one that can give us recommendations about what kind of structural modification could help us to reduce the HERG liability of our compounds. So, for example, if I go back and replace this chlorine atom with a methoxy group, then I find that the predicted HERG value is 4.54. And let's see what the HERG assistant tells me. How can I try to decrease it? I find some modifications that I could try. For example, replacing the methoxy group with this pyridine-based one. And actually, it helped to slightly decrease the predicted HERG PIC50 value. So it was a good recommendation, and I will also save this molecule as a new draft compound. Another thing that we have to pay attention is whether there are already existing assay data for the compounds that we are designing. We could use the Campbell activity plugin for that. In the case of these molecules, the plugin couldn't find any matching structures with existing assay data, but I will keep the plugin open so we can check it from time to time. And after that, we can try a couple of other aromatic rings on our compounds. So let's try, for example, an indole ring in this position. Putting a nitrogen here and double bond, and see how it could work. And the plugins are saying. And if we want to get some further ideas how we could modify, what kind of other modifications we can try, then we could use the Enamine search plugin that is called Enamine 1212. And this is the plugin that can run similarity and substructure searches in the 1.2 billion compounds that I found in the Enamine Real database. In the meantime, I also making some modifications in my layout to display the plugin and the results that it gives. So the search results that were found in the Enamine database tell us that the closest analogs that were found all contain the same aromatic ring without any modifications. So what we can try instead is simplify the molecule a bit and remove the nitron part and check only whether we find any kind of close analogs with this smaller building block. So if we browse the search results of the Enamine plugin, then we find that indeed there is a methyl substituted ring in the database, and also there are some quinoline or isoquinoline containing building blocks available. So by continuing browsing the Enamine compound, for example, by loading this methyl substituted variation and removing this other methyl group, then we could get step by step, we could get further and further from our initial idea and explore other parts of the chemical space around the molecules. And once we have found that we have a good scaffold, a good core idea that we would like to investigate further and in more details, then we can quickly create a series of compounds with the help of Design Hub. For this, we can use the small-scale enumeration feature. So what we will do now is that we will use this indole-derived core structure and give and draw back the original or the previously removed part of the molecule, the nitron part and the tert-butyl group at the end. And then what I would like to do is have a series of compounds where we use different functional groups to substitute this indole nitrogen. So I will add an R atom here. And in this position, I would like to try different alkyl groups, for example, a methyl, an isopropyl, or a butyl group, but I will also have the unsubstituted, or I also want to have the unsubstituted compound. And then I will add also, I will create the first R group from them and add the attachment points to them. And then I will add, I also would like to use different functional groups in one of these two aromatic carbons. So I will continue drawing my Marcus structure. I added one substituent variation to the indole nitrogen, and I would like to add now a second one to one of these aromatic carbon atoms. So add this group first, then a simple fluorine atom, and a trifluorocarbon can be added as well. And then I will create the definition of the second R group from these three functional groups, and also add the attachment points to them. And once I've finished drawing this Marcus structure representing this small library, I will get the enumerated structures in the library from Design Hub. And while I was sketching the Marcus structures, the plugins became disabled. But now if I select one enumerated structures, that they will activate themselves again and display the result of the currently selected one. And if I want to, I can select one or two enumerated compounds, or if I want to have all of them, I could save the entire library, all 24 enumerated molecules, and add them to my collection. And after this, we can continue checking the properties of these compounds. We can check, for example, if we could purchase any of the molecules from one of the supplier companies. We could search, for example, in the Enamine database and check whether this molecule can be found there or not. If we found that there is no hit, no result coming from the Enamine catalog, then the next step that we should try is simplifying the structure of the molecules and use, instead of that, a building block, for example, remove the nitron group and replace with a hydroxyl group. And there are still no result in the enamine database. So we can continue simplifying the structure, for example, removing this chain and replacing the amide ring with the carboxyl group. And maybe with these substituents, we couldn't find the molecule, but if we remove one of the substituents, then we may find something, or we may find the molecule in the enamine real database, and this way we can get access to one of the building blocks of the compounds that we would like to synthesize. So after this, we could continue collecting new molecules and checking their properties. But we would like to also give you some time to try one of the plugins that we have now used and you have seen, or also some of the other plugins that you can see in the property collection. And you can create your own design sets, your own virtual molecules, while we will having another few minutes break and check again the Q&A section. And after that, we will be back for the third and final part of the workshop. So welcome back for the third and last part of the workshop. During the break, we checked the Q&A box, and there were a couple of questions which were answered in written form. However, there is one of them that I think would be interesting, so we would like to answer it live or repeat the answer live as well. So the question was about speed and if there is any issues that could be expected with scalability and the speed of retrieving the results. There are a couple of aspects of this question. For example, the Campbell plugin that you have seen here is in a public service, which is operated out of the UK. And from time to time, it becomes unavailable. For this purpose as well, it could be useful to have a private copy instead and use that for the plugin. With the non-public services that you have seen here, the calculated properties, the MPO score calculation, the Payne's filters, Hergas instant, and the other ones, typically it takes 1 second per molecule to calculate those values. And the case is if there are around 100 chemists, then this 1 second will not really change because this is a very short duration, and it is very unlikely that the calculations, this 1 second long calculations, will block each other. We use this method, this solution at customers with more than 250 chemists, and no such issues were encountered so far. So the scalability is not a real issue here. And besides that, in one of these ChemInfo Stories webinar series, there was a presentation on AWS Lambda functions, which could be interesting as well to have a high-level understanding of how we can use these very cool and very efficient cloud services, cloud technologies to further accelerate the work and further accelerate these calculations. In the Q&A box, you can also find the link to this AWS Lambda related presentations. So please continue adding your questions. Our panelists are quite eager to hear them, and also the product manager of Design Hub is among them, and he is really quite interesting to hear your opinion and your questions. And now let's get back to our workflow. Let's see what we can do next with the virtual molecules that we have created. We have now more than 20 compounds that we have drawn or created with the small scale enumeration. So the next step would be to prioritize them and select which ones should be taken to the next stage, which one should be selected for synthesis. For this, I went back to the overview mode, the design set overview mode of the application. And here in this overview mode, you can see each virtual molecule on its own card. And to get some help with the prioritization, we can use the same properties we have used previously in the design mode. We can add, for example, some PhysChem calculations like the mass or polar surface area or the strongest basic pKa values. It would be also useful to have the MPO score here as well. And also the predicted hERG value of the molecules could be added. If we have more than a couple of properties that we would like to see on these cards, it could be handy to switch to a spreadsheet view and see the properties in their own column. And now what we can do is we can use these properties to filter our compound collection. For example, we can use a structure-based filter to select only the indole-containing molecules. So for this, we can use a substructure filter. There are 24 of them, the ones that we have enumerated. And then we can also add another filter based on the MPO values. Let's say we only want to keep those ones in the list which have a MPO score of at least 5.5. And finally, let's add the hERG prediction. And let's say we want to have only those ones where the hERG PIC50 is less than 5. So this gave us 14 compounds that meet these criteria, and we can also sort them based on, for example, the hERG PIC50 value. So if we sort them in ascending order, then we see at the top of the list the least risky ones, let's say. So after this, we can say that for now we will select the first 8 compounds and give these first 8 compounds the highest priority. And these are the ones that we want to have synthesized first. So I will change their status to for synthesis. And then we can select the remaining the remaining compounds in the collection and give them medium priority, but say we also want to have them synthesized at one point. And before we go to the next stage, we should also share these so far private series, this private design set with the rest of our team. And why these compounds become public and the design set becomes public, Design Hub will also check the virtual molecules to see if there are no structural errors or drawing inconsistencies in them. And also they will check whether they are unique virtual compounds. No one have saved them in any public design sets previously. And for the unique compounds, it will generate the new virtual identifiers that you can see here. Okay, so and then we can also switch off the filters if we want to see all the molecules that we have here. And as a result of the design set becoming public, all the other compounds have been promoted to the ready for review phase. So later on, after the first round of synthesis have been finished, we can return to them and decide if we want to refine them further, or if we already have enough information, or if we want to put them on hold or cancel them. And to have this overview possibility and from time to time to check how the compounds and the design set is progressing, we can use the Kanban board of the application. So if we check the Kanban board at compound level, then we will see each virtual molecule in a matrix where the molecules are organized based on their current priority and their current status. So here we can see every compound that can be found in the acetylcholinesterase related project. This means at the moment 3 hypotheses. But if I want to, I can select just one of them that we have worked at this point. And I can add some information. So once the synthesis of some of these compounds have been finished, then I can drag them to the synthesis completed column. Or if there are some other ones which are still getting prepared, then they should be put to the in synthesis column. Or some of the molecules may be put on hold for a while, which we can also indicate here. We can also combine the board with different filters, so to find only certain molecules with molecules that contain a certain substructure. Like the methyl substituted ones, and see how they are progressing so far. And if we want to have a similar overview at a higher level, for example, at the level of the hypothesis or the design sets, then we can go to the hypothesis level, for example, and see and switch to see all my project hypotheses from all of my projects. And here again, I can filter the design set. I can switch to the same Kanban board, or I forget that, and I can filter the hypothesis collection to based on some status or assignee information, or based on the text that I have used and added to them previously. and see that now we have our new hypothesis in ready for review state, but if we want to, we can get it to the next phase, to the in progress phase, and indicate that the synthesis of the molecules have already been started. And with this, we are at the end of the workflow that we plan to show you today in this workshop session. Finally, let's check again if there are any new questions in the Q&A box. As far as I can see, we don't have any new open questions at this moment. However, as I mentioned at the beginning, this demo environment will remain available for you for 2 more weeks. So please, if you found anything here, return in one of the following days, log in again, and try out these features again. We are, of course, quite eager to hear your feedback and your questions. So if you liked the topics that I have mentioned or some of the solutions raised your interest, then don't hesitate to reach out to us, either an email or discuss those topics further on our LinkedIn group. And we also hope to see you in our upcoming webinar next Tuesday, where we will look into IP and Marcus structure related stories. You will see the link to the events page in the chat window shortly, along with the link to our community. And now finally, in the name of the speakers of the webinar series and the team working on the ChemInfo Stories series, I would like to thank you for your time and your attention. Bye-bye.